Recording is rolling. It is Monday, April 14th. I have a PowerPoint for you guys today on thermodynamics. We'll get most of the way through it. You guys get to learn a bunch of funny concepts. So that's what we're doing this week. We're just going to take a few days, do some light learning on thermodynamics. Now, my different classes, conceptual and honors, might be a little bit different things with them, but yeah, probably just a few days, maybe a week. Well, to be honest, right? There is some school-wide testing going on tomorrow. FCLE, I think it's Florida Civics Literacy Exam. Okay. So if you think that applies to you, if you take some civics class, it's mostly 10, 11th grade, I think. Right. Anyway, I think there's some Excel files floating around, so double check, make sure. But as far as I know, I think this class is just going to be a normal class. I think almost all my students are going to be here. So if you're not in class tomorrow, you can just watch the tomorrow's video, and I think it'll be good to go there. Okay. So I think tomorrow it's going to be kind of like today's. Just presentation, PowerPoint, some demos, that sort of thing. All right, so let's jump into this. Thermodynamics. Thermodynamics. All right, so start with how do you measure temperature? And you might remember way back at the beginning of last semester, I said, well, how do you measure anything? And we were trying to come up with ways to measure stuff. And all of first semester was really just 3 units to boil it down to. That was mass in kilograms, distance in meters, and time in seconds. So from that, you could make momentum units and energy units and that sort, right? But a separate unit was temperature in Kelvin. One you did recently was electric current. That was also separate from most initial things. Okay? Now, nowadays, we do have a kinetic energy theory of temperature, which goes like this. Is if you transfer some thermal energy into something to heat it up, down at the atomic scale, those molecules are vibrating faster and faster. And if you cool it off, you're taking thermal energy out of the system. The vibration of those molecules slows down. Okay? But if you go back, say, hundreds of years ago, where people had the idea of atoms, but there just wasn't the technology to do the scientific experiment to verify that atoms existed, okay? It was kind of a mystery as to how exactly did temperature work. Okay? But eventually, people started developing scales. So you could just, rather than just say, oh, it's hot or it's cold, you could start to quantify. Right? Like, maybe I know at this temperature, water changes phase, maybe it boils, whatever, right? But what about that same temperature to other materials, or how much temperature does it take to melt copper, and how does that compare to boil water, right? How do you make those comparisons? So the first, I'll go historically. The first scale that came around historically was this Fahrenheit scale, which of course we still use in the States for temperature. So we grew up learning this one. Okay. There's a wacky history of where the numbers come from. It has to do with like human body temperatures, and he rounded to the nearest. Right. But anyway, I bet you guys know this one is what temperature does water freeze and boil? Or sorry, freeze and melt in Fahrenheit. Yeah, 32, right? 32 degrees Fahrenheit, right? And what about boiling? How much does it take to boil water under a stove in Fahrenheit? Yeah, 212, right? Although that's really only true down here in Florida at sea level. If you go up in the mountains, that changes. Maybe that'll show up the next couple of days, but at sea level, these numbers are true, right? Okay, so now we finally have a system where we can quantify how hot or cold something is. Well, it's kind of a wacky system, right? Now, eventually, when the metric system comes around, you guys remember the metric system, which we use all the time in this class, is to say, well, let's come up with a more like universal system of units that are based on properties of water, if we can. Like the original definition of a kilogram was how much water is in a 10 by 10 by 10 centimeter cube. Can we have everything numerically based on like factors of 10? That's nice. We can just scale up and down by factors of 10. So what came out of that thought process is the Celsius scale, where water freezes and melts at 0 degrees and boils at 100 degrees. Again, that's only true for 1 atmosphere of pressure. We'll get to that later. Okay. Little historical side note is the original version of the Celsius scale was actually upside down. He said, hey, let's have water freeze at 100 and boil at 0. Ah. And right after he died, everyone was like, that makes no sense. They just turned the scale upside down and made something that makes a lot more sense. Right? Right. But that system, that Celsius system, still has a flaw, which is that it's a relative system, just like Fahrenheit is a relative system. Fahrenheit, Celsius are both relative, which means they can both go negative. You can have negative temperatures in both Fahrenheit and Celsius, but it's not like there's a physical negative amount of anything. The negative just means it's below the freezing temperature of water. Well, in the case of Celsius, that's true, right? If you have negative 10 degrees Celsius, it's just colder than the point that water would freeze or melt, right? But if you have a material other than water, then it's like, well, there's nothing special about having a negative temperature. Right? Also, later today, we're going to apply some equations to entropy and to ideal gas law. You'll see a little bit today, where if you scale up and down temperatures by some factor, say if you want to double the temperature, then that makes no sense in terms of relative scale like Celsius or Fahrenheit. For example, guys, how about this? What if you go from 10 degrees Celsius to 20 degrees Celsius? You guys got that? 10 degrees Celsius to 20 degrees Celsius. Did you just double the temperature? Yes or no? Ah, so you guys shaking your head. You're on to that. The answer is no. Right? In proportion to like all the internal thermal energy that object had, it only went up by a tiny factor. I think it's like 3 or 4%, something like that. And that matters when you deal with, say, ideal gas law. It's like, how much does the balloon expand when you heat it up? Because that you need some kind of factor. Anyway, what I'm making the case for is we need an absolute scale, and that's where the Kelvin scale comes from. You guys see this Kelvin scale on the far left, right? So this is the most recent one. This is really the most useful one for the equations that you guys are going to see this week, right? Because this one starts at absolute zero as 0 Kelvin and then scales from there, right? And absolute zero is the coldest you can get in the universe, right? It's like where you take all the thermal energy out of something, you completely deplete it, and it's left with 0 thermal energy. That corresponds to 0 Kelvin. Okay. Now, in the laboratory, scientists have never reached true 0 Kelvin, but they've reached, like, I think, like a billionth of a degree above that or something. So some crazy refrigeration and laser process or something, right? So something like that, right? So 0 starts at 0. 0 Kelvin is absolute 0. Okay. Now, what that means, see if you guys get this. Suppose you go from 100 Kelvin to 200 Kelvin. Did you double the temperature there? How many guys say yes, from 100 Kelvin to 200 Kelvin? How many guys think that's truly doubling? Yes, it is. Yes, it is. Right? And suppose you had a balloon and you heated it up from 100 to 200 Kelvin. Would it expand to also twice as big? Yep. And that's ideal gas law. You guys can see it later today. Oh, so it all checks out. Okay, so you guys good? Good. Right. One more detail on Kelvin compared to Celsius. You guys see that these two scales are actually scaled the same, like in terms of a temperature change. Guys, watch this. You go from freezing to boiling for water. That's from 0 degrees Celsius to 100 degrees Celsius. Look what that is for Kelvin. From 273 Kelvin to 373 Kelvin. You guys see it's also a change of 100 units, right? So a change in 100 Kelvin is the same thing as a change at 100 degrees Celsius, right? Notice I'm saying Kelvin, not degrees Kelvin. It's a little technical thing, right? Or for later today, I'll put some math puzzles and I'll ask you guys, is it okay that a change in 1 Kelvin is the same thing as a change in 1 degree Celsius? And sometime later in class today, you guys are going to remember that that's the same thing, okay? You guys remember that? Okay, hold on to that. Right, so now we have ways to measure temperature. Okay, so with that established, let's fast forward to about the late 19th century when people were coming with new machines related to the recent industrial revolution, the steam engine, figure out how to what's the mathematics involved in the steam engine, right? And through this process of trying to figure out how machines operate, how to get useful work, and how that compares to the energy input, right? Got to either have like some river turn a water mill or have some lump of coal I can burn to make something move, right? They eventually outlined these laws of thermodynamics, right? Okay, so let's go through these one by one. So the zeroth law. Now, the zeroth law is one that's maybe so obvious you might not even think of it. It just says if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. All that basically means is if two objects have the same temperature, then they're not going to transfer energy to one or the other, right? So like if this house has the same temperature as this car and you put them side by side, then there's no thermal energy transfer. That's all, right? If you have a ball on top of a plateau, it's not going to roll downhill if there's no downhill to roll down, right? Right. So I'm probably not really going to mention that one so much again. It's just like so obvious, right? Right. If I ask you guys any questions off this slide, say on the final exam, which is coming up in a few weeks, it's probably going to be the first law and the second law. You'll get questions about those, about the first law of thermo and second law of thermo. And the first law you already know from last semester because it's just conservation of energy, which says you're allowed to change forms of energy, but you cannot create or destroy energy. You guys remember last semester creating conservation of energy equations? Ball rolls downhill. It starts at the top with potential energy. It ends up with kinetic energy, and then so on. Things like that, right? Now, this week, we're bringing in a new form of energy, which is thermal energy. There's some equations with that. You guys will see some equations later, real short equations. Like how much thermal energy, what does that have to do with temperature? That's all right, right? But the number of joules that goes into heating something up, cooling something off, right? You cannot create joules of energy. You cannot destroy joules of energy. You can just transfer the energy from the coal. I burn it, boils the water, turns the steam engine. Blah, blah, blah. Okay. Right? All right. You know that one already. Now the second law. Okay, this is where things get real crazy. Right, you guys ready for this? You guys ready? Have your brains definitely turned on? Right, things get real abstract here. I have a lot to say about the second law of thermodynamics. This one has a lot of consequences. In fact, some of the things I have to say, we won't even get to the slides today, but tomorrow where we pick up at the end of this presentation. Oh, say, do you guys remember the second law? Okay, so here we go. So what does it say? Okay, entropy of an isolated system always increases. Okay, what does that mean? What is entropy? What is this? Right. But this diagram right here says a lot. If you have, say, like a hot sink next to a cold sink, there will be spontaneously a transfer of thermal energy from the hot to the cold. And the hot's going to cool down a little bit, and the cold's going to warm up a little bit, maybe until they reach equilibrium, right? Something like that happens, right? Now, that's a spontaneous process. Would you ever expect to see that process happen in reverse? Like, what if I have lukewarm next to lukewarm? Is one object going to spontaneously transfer thermal to another and heat up while it gets cold? Is that ever going to happen? No, not spontaneously. Now, you can force that with refrigeration, but refrigeration is not a spontaneous process, right? It takes some effort into it, right? Right. So there's some equations that relate to this. And what does this word even mean? What is entropy? So again, this is a really abstract idea that people figure out, hundreds of years, well, a couple hundred years ago, just by working with machines. You could think of it as the unavailability of energy to do useful work. Right? So like another consequence of the second law of thermo is, say you put a gallon of gasoline in your car to make the car go, right? Doesn't that gasoline have a bunch of energy and chemical bonds? Right? Now, it turns out only about 30% or so of that chemical energy in the gasoline actually makes the car drive across town. Right? And the other about 70% goes into waste heat. Right? You guys ever feel the engine of your car after you finish driving it? It's like really hot. Like, I don't even want to touch that. I have to let that cool down. Right? The engine's really hot. Right? Because a lot of that energy went into waste heat. Now, that's not really useful, but it's inevitable. Right? So that's related also to the second law, right? And that waste heat, could you ever sort of recapture that and also make the car run, which would be useful work? Well, not really, no, right? So there's some efficiency of your car engine that will never reach 100%, and definitely can't go over 100%, right? Yeah, so your car engine's about 30% efficient, thereabouts. Right, third law, look at this one real fast and see entropy of a system, right? So that unavailability of useful energy to do work, energy to useful work, right? Right? Approaches a constant, so maybe like a horizontal asymptote as the temperature approaches absolute zero, right? Which may be like a special laboratory condition. Okay, well, right, probably won't ask too many questions on that, but okay, it is what it is. Right? But, you guys got on the slide so far? Okay. Okay, so I have lots of slides related to the second law, so let's see what I got queued up next. Okay. All right, here we go. So this is what I was just saying before, but this is even better. It's got a visual. Say you got a hot sink next to a cold sink, maybe two aquariums. Right? Now, if you leave that alone for a few hours, could you come back and they reach this equilibrium, 50 degrees, 50 degrees, right? But again, if you start off with that picture on the right and left it alone for a few hours, could you ever come back and it spontaneously turns to that picture on the left? No, even though the first law of thermo would still be safe, right? You're not violating conservation of energy, you would be violating the second law of thermodynamics, which says something about the increase in entropy in the universe. Right? Now I have some equations go with this, and I want to write an example with you guys too. Does it show up? Okay, I'm going to go backwards. I know I skipped a slide there, but you guys see a couple of equations down here? I'll show you guys what these mean, and we'll do a numerical example. So this delta S, this means the change in entropy. Right? Here, I should read this bullet point. Second law of thermodynamics. Second law states that the total entropy of an isolated system, or sometimes you see it like as the universe in total, always increases or can never decrease, right? And entropy is thermal energy per unit temperature that's unavailable for doing useful work, right? So we're going to call entropy capital S. You guys see capital S? So when there's some process, right, like a hot sink transfers thermal energy to cold sink, that's a thermodynamic process. The change in entropy that results, right? Well, I can quantify it by doing the transfer of energy in joules. That's what delta Q is. It's a change in energy. So this week, capital Q is thermal energy, okay? Divided by the temperature this all happens at. And this temperature, what do you think you can plug in for a temperature? Fahrenheit, Celsius, or Kelvin? And only one of those can work. Which one? It has to be what? Kelvin. It has to be Kelvin, right? Because it wouldn't make sense in a relative scale. Like if it was negative 10 degrees Celsius, that wouldn't even make any sense, right? Right. And the second line right here actually is a mathematical way of stating the second law of thermo. It says the change in entropy over change in time. So as time progresses forward, what happens to entropy in the universe? It's always greater than or equal to 0. Right. Now, that's not necessarily true for every individual object, but that is true in the universe in total. So here, I'm going to go back a little bit, go back. Right, let's do a numerical example of this slide right here. Well, I'll change the numbers a little bit because I'm just going to copy my notes from earlier today. Let me get this out. Okay. Yeah, I'm looking at this off screen. Okay. You guys got some paper out for some notes along with me here. We'll just do a couple pages notes today. Okay. So say I start off with a couple of blocks here. Okay. I put my own numbers, just went up. So we'll do a before and after picture. So I'll get a before the thermal energy transfer and an after. Maybe like at 1 o'clock and 5 o'clock or whatever. Let's say that these start off at 50 degrees Celsius and 30 degrees Celsius. Okay. Now, if it's the same mass and the same material, do you think they're going to probably meet right in the middle at 40 degrees Celsius? Right, so 40 degrees Celsius and 40 degrees Celsius. Right. Or if they were different masses or different materials, it'd be somewhere in the middle, maybe 32 degrees or 45 degrees, but it'd be somewhere in the middle. Right? Okay. Now, once they reach thermal equilibrium, doesn't the process of heat transfer just come to a stop? Okay. So that's right there. Oh, I'm going to write that. I'm going to say, I'll call this the left box and the right box, or aquarium or sink, or those are all terms that are used. Okay. Let's say there's a delta Q, a transfer of thermal energy from the hot to the cold. Okay. And then at this picture right here, these would be in equilibrium. Thermal equilibrium. Okay. Okay. And then process comes to a stop. Okay. Is that okay so far? Okay. Okay. Now, you guys know delta Q is a transfer of thermal energy. Right? So Q, capital Q, this week is going to be thermal energy, some number of joules. We throw the delta, you guys know delta means change in this case, a transfer. Okay? And I need to come up with a number of those just to run a numerical example with you guys. Let's just call it 100 joules. I don't know, right? If I told you the mass of water and the specific heat of water, you'll see those terms later, you could probably calculate that. I'll just throw a number at it. Okay? All right, then delta S. Okay, here's delta S is going to be the change in entropy. Remember, this is that concept of the unavailability of energy to do useful work. Okay? It should be on the rise, but let's see. So the formula goes the transfer of thermal energy, which could be some number of joules, divided by, okay, so that's this one right here, or divided by the absolute temperature that this all happens at. So I'll label this, well, I'll call it absolute temperature. Absolute temperature. Like you guys just told me a minute ago, I have to plug in some number of Kelvin to make that work. Because Celsius wouldn't make any sense, because it could go negative, it's a negative thing. Right, so it has to be absolute, it has to be Kelvin. Okay. All right. So let's say got some space at the bottom of this page. I can fit this all on this one page of paper. So I'm going to do that. Okay. Let's solve that right there. I want to know what happens in terms of entropy. So entropy right there. What happens in terms of entropy? Okay. So I'm going to do this for each individual box. Remember, I labeled these boxes the left box and the right box. Okay. And then we'll say what happens to the entropy for the entire system. Okay. So delta S, the change in entropy of the left box. We'll set up an equation for that. The equation is going to look like this right here. Go to your writing formula. Okay. We'll do what's the change in entropy for the right box. And then we'll say what's the change in entropy for the system. Or I'm actually going to throw a subscript on here that says universe, which is a common thing to do. Because, I mean, this is for the system, which is a closed system. That's how much for the entire universe it would be also. Okay. And what we're going to get for the universe is we'll calculate it for the left box and also for the right box, and we're just going to add them together and see what happens. Okay, you guys get that concept? Okay. So while you guys are finishing jotting this down, recap what we got so far. I got a cold sink next to a hot sink, or a cold box next to a hot box, or sorry, hot next to cold. Okay. The hot box is transferring thermal energy to the cold box, and so the hot's cooling down, the cold's warming up until they reach an equilibrium. Okay. Now the transfer of thermal energy leaving the hot is exactly acquired by the cold. Okay. So that's conservation of energy. Okay. And the target question, which I'm going to do some math down here, is how does the entropy for the system change? Which is going to be the transfer of energy divided by the absolute temperature this all happens at. Right, all good? Okay. So let's set up this equation right here. So I know that the left box, which was the hot box, is going to lose 100 joules, because that's what this is right here. I just made up a number. So that 100 joules, loses 100 joules, so that's negative 100 joules. Okay. And this happens at what temperature? Well, okay, now here's where it's a little tricky. I'm going to make a little simplification. Because doesn't it during this process go from 50 to 40 degrees Celsius? Is that true? So if everybody gets this exactly right, shouldn't I really do like 50 degrees? Maybe divide this into 10 intervals and do like 50 degrees and 49 degrees and 48 and 47, do that all the way down to 40. Right? But can I kind of say it's on average going to be about 45 degrees over this whole process? Is that okay? 45 degrees Celsius. So to make that an absolute temperature, I have to add what? How do you go from Celsius to Kelvin? Did I tell you guys that? There, I'll write down here. There. So temperature. Hold on a minute. I gotta have a poster for this. I got a bunch of posters. I haven't even broken those out today. Let me dig it up real fast here. I know it's somewhere in here. Is it this one? It is. All right. So here's my own poster for temperature scales, right, which you guys just saw earlier today. And here are some equations. So I gave you guys a bunch of Celsius, but the equations don't work unless you use Kelvin. You have to add 273. You guys get that? And change, but we're going to ignore the change. We'll just call it 273. Okay. Oh, while I got this one out, by the way, if you ever go vacation anywhere outside the States, and you want to know what's the weather like outside, say, oh, it's a jolly 18 degrees outside. And you're like, well, what? Right? Then that's what this blue formula down here is for. Take their temperature times 9/5 plus 32. That'll give you the American temperature. All right, but we need this one right here. We're going to add 273 to get to the absolute temperature in Kelvin. So 273. Right, that's how many Kelvin. Right. Which, by the way, if I did that for every individual temperature, 49, 48, 47, all the way down to 40, it's not going to be a whole lot different. Right? But if you want to get it exact, then that would actually be a little bit of a calculus process. Then I'm just going to simplify it and call it 45. It's not going to change the answer that much anyway. Okay? Hey, what about the right box? Doesn't the right box gain those 100 joules? So plus 100 joules to the right box. Okay? And what's sort of the average temperature of the right box during this whole process? It goes from 30 to 40. Can I kind of estimate at what? About 35 degrees Celsius, right? Okay, so I'm just going to do that, 35 degrees Celsius, right? Plus 273 to turn it into an absolute temperature in Kelvin. All right, okay, you guys good so far? Okay, so the hot box is cooling down, the cold box is heating up, they're reaching equilibrium. And how does the entropy change for each individual box? Well, 200 divided by 45 plus 273. So the left box, which is cooling down, lost 0.314, that's joules per Kelvin of entropy. This box on the right, which is warming up until it reaches equilibrium, that's 100. It gained 100 joules of energy. So divide by 35 plus 273. This is plus 0.325. That's joules per Kelvin. Okay, all good so far? Okay, that's right. Right. Okay, so the hot box cooling down, losing entropy. The cool box heating up, gaining entropy. But is that an equal amount of entropy? Yes or no? It is not. It's a mismatch. So if you want to know what's the change in entropy for the universe, all you have to do is add these two together and see what happened for the system. Let's see what that is. That's 325 minus 314. So that's plus 0.011. That's joules per Kelvin. There you go. Right. So what that means is you put this hot box next to this cold box, or hot sink next to this cold sink. Let it run until it reaches equilibrium. Okay. All the energy was conserved, but the entropy of the system and therefore the universe had to increase. You guys see that? Okay. And you know what? It doesn't matter what numbers I pick. I know I just pulled these numbers out of thin air, these temperatures and this energy transfer. I could have made up anything. As long as the boxes reach an equilibrium temperature, you could plug in numbers all day. The change in entropy of the universe will always come out to be a positive number. You see that? Okay. Now, what does that mean? That means that as the universe gets older and older, as time moves forward, right? See, there's an arrow of time. I forget, it's later in the day. That last semester, it's kind of hard to tell whether processes are happening forwards or backwards, right? Conservation of energy, conservation of momentum. Throw a ball in the air and goes up and comes back down. Right? What's forwards and what's backwards? What came before and after? Right? But now we're getting at the question of like, how do you sort of demonstrate an arrow of time? Right? Like this top picture always turns to this bottom picture spontaneously, but never the other way. How can you show that mathematically? And this is the answer. So the property is entropy that always increases. Right? So another way to say that is even though the quantity of energy in the universe is conserved, that's the first law of thermodynamics, the quality of energy in the universe is always decreasing as time moves forward. Okay. So back to here. You guys all right so far? Who's got any questions? Any questions? All right, let's check this out. All right, here's another perspective. We'll go through a few perspectives on entropy. So thermodynamic quantity representing the unavailability of energy for useful mechanical work, right? Often interpreted as the degree of disorder or randomness in a system. Okay? So here's a little bit different perspective. Sometimes you hear like, if you don't make an effort to keep your room clean, it'll naturally get messier because you're not putting things on the shelf, right? But let's look at the sandcastle. This is a really common example of this sort of macroscopic example of entropy. Right? Say you go to the beach and you build this nice sandcastle. Isn't that like a highly ordered arrangement of those sand grains? Right? And then, okay, you leave that alone and come back, let's say a few hours later, and by then it's turned into just a random pile of sand. Like that could naturally be expected to happen spontaneously. Isn't that true? Right. But what if you just had like a random pile of sand? It's like, right? You walk away. Right? Let's say there's no one else is visiting the beach. Could you come back a few hours later and it spontaneously turns into a nicely ordered sand castle? Is that ever going to happen? No, not because like the wind couldn't move every grain of sand to. But statistically, probabilistically, it's never going to happen. That would just be a crazy event to happen, right? So in terms of like individual molecules, you can think of it like the molecules going from a highly ordered state to a less ordered state, right? If you have a bag of blue marbles and a bag of red marbles, and you throw them all into one giant bucket, right? They're not going to naturally separate out. They're all going to mix together, right? And if they were mixed together, you couldn't just shake them and they're going to naturally separate red and blue. Just probabilistically, that would be a crazy thing to happen, right? So with that, now you might think, well, hold on, I could take this random pile of sand and I could create the sand castle. Isn't that decreasing the entropy of the sand? And that's true. That go from the picture on the right to the picture on the left. That would be decreasing the entropy of the sand. So then what did I just break the second law of thermodynamics? Does just simple human effort break the second law? Right? And the reason that it doesn't, the second law of thermo is still safe, is because by you moving the sand, you have to move your muscles, and there's some energy expenditure there. And if you include the increase in entropy of moving your muscles around, or if you're operating a machine or a robot, if you account for that increase in entropy, that will always, always, always outweigh the decrease in entropy by ordering the sand molecules. It always happens. Okay? Now, remember, I've been using the word probabilistically and statistically. So if you get small enough, like if you get like 5 or 10 molecules, do you guys think that down at that scale, like just 5 or 10 molecules, it's possible sometimes the cold one transfers more heat energy to a hotter one? Could that happen? Yeah, right. Now, doesn't usually happen, but it can. So the second law of thermodynamics, the one that says entropy is always increasing. This is sort of like a breakable law of physics, but only in like really small scales and really rare instances. But does it ever happen on an aggregate scale? Not that anybody's ever seen or figured out a way to break this law. Right? So not that we know of yet. I don't know. Maybe 10,000 years from now, people will figure out how to break it. I don't know. Maybe not. But it's not right. It's sort of a breakable law that never quite gets into it. All right. Okay. You guys saw this slide before too. All right. I was pointing out these equations, so we were just using these equations. So remember, we just applied this. I threw some numbers at this one and show you guys change in entropy for, say, this hot sink, this cold sink, and then collectively. And collectively, this delta S always has to increase spontaneously. Right? And this bottom line, that's exactly what this bottom line says, right? So the change in entropy as time moves forward can never be negative. It can be zero positive, right? So here's another consequence of the second law of thermo. What if you blow up a balloon? So you got high pressure inside and atmospheric pressure on the outside, right? And then let it go. All the air is going to evacuate the balloon, right? But if you just had a balloon lying around, is it just going to spontaneously fill itself up? No. I go from a higher entropy to a low entropy state. Right? So that's another example of the second law of thermo. Right? Now, of course, you can force the balloon to blow up, or you can blow it with your lungs. You say, hey, look, I just decreased the entropy of the balloon. Did I just break the second law of thermo? And the answer is still no, because don't forget that your lungs are doing a bunch of work. So if you also account for the increase in entropy in your lungs, then that will always outweigh the decrease in entropy from the balloon being blown up. Okay. All right, let's talk about heat transfer. There are three main forms of heat transfer. You guys probably learned about these in past science class, maybe elementary, middle school, or something like that. That's good to know for sure before you get your high school diploma. So three main forms. So first one is conduction. This is direct contact of surfaces. That's like what I was just showing with those two sinks if they're just side by side, right? So you touch this handle of this pot and it feels warm. That's heat transfer from the pot handle into your hand. There's some thermal energy transfer there, some number of joules, right? Second one, convection. So for convection, you need bulk movement of molecules. Usually some kind of fluids are involved. A fluid could be a liquid like water. A fluid could be gas, could be air, right? But there's going to be a temperature differential. And because there's a temperature differential, the warmer fluid is going to want to take the place of the colder fluid and vice versa, right? And then it gets that motion, which is going to transfer heat energy that way through convection currents. Okay. And third one is radiation. So say if you put your hand nearby the stove range, don't touch it, of course, right? But you can feel this heat radiating off. Right? Hey guys, which of those three right there, conduction, convection, radiation, which is the only one that can go through the vacuum of space? Huh? Radiation, right? Radiation. Right? Isn't that how sunlight gets to the Earth through the vacuum of space? It's just radiation, right? Electromagnetic radiation. You have your infrared, your visible light, your ultraviolet. Yeah, right. Not all radiation is what's called ionizing. That's the kind that can like give you cancer or whatnot. But yeah, electromagnetic radiation right there. Right? I've seen some textbooks also have a fourth kind of heat transfer. I forget what it's called, but it's like it's kind of like convection is applied to solids. If you have a hot block and move it across the room or something, I don't care about that one so much. But all right. And so speaking of convection, let's look at these convection currents that are set up around the world. Okay. Also, this is a Sunshine State standard. You guys are supposed to learn about this just separately anyway. Okay. Here, I'm going to flip the screen. I got a trivia question for you guys. Do you guys have a world map visualized in your mind? Because I don't want you guys to be looking at it while I'm asking you guys this question. Okay. So imagine England. Can you guys imagine where England is on the map? Now cut straight across to North America, the same latitude. Is what's at the same latitude as England, but over North America? Canada. Yeah, let's look at this again. So here's England way up here, cut straight west. Ooh, the frozen tundra of Canada. What? How can that be the same latitude? It's like hundreds of years ago when the first pioneers were coming over, the first settlers, they had this idea of, okay, well, no, it's colder climates in the north and it gets warmer as you get closer to the equator. Right? So they were not expecting, so let's say like Massachusetts, that they were going to have these harsh winters because it's Massachusetts is way more south than England, and England's kind of a temperate climate, okay? But no. So there's this other factor of these convection currents. So in this case, the Gulf Stream, right? The Gulf Stream, which comes right by us. You guys ever go out to the ocean here? And if you're just kind of drifting in the ocean, or if you throw a beach ball there, you guys see it kind of drifts towards the north. You guys ever notice that? because the Gulf Stream right out there. Okay? That's carrying a bunch of warm water and warm air all the way up to north of Europe and keep it from looking like a frozen over tundra like Canada. Right. So what's driving these currents? So there's three main drivers of the currents. One is temperature differences. Right. So it's like going back to this right here, like this temperature differential here between the hot and the cold. Right. So gets warmer to the equator, colder to the poles, got a temperature differential, drive the current. Okay. How about this? Oh, as if the sun is, do you think the sun is probably evaporating water faster near the equator than near the pole? Right? Because more solar flux near the equator. But what actually evaporates? Is it all the salt water? Or is it just the water constituent? Is it just the water evaporates? Does it leave behind the salt? Ah, now you have a salinity differential, different levels of saltiness. That also helps drive the currents. I don't know what proportion, how much these are weighted, but so we got a temperature differential, we got a salinity differential, and the third one I've read is wind. So like as the Earth rotates, and you guys remember like Coriolis effect from back in the day too. Yeah, there definitely is some Coriolis going on here. I forgot to mention that earlier at my other classes. But do you guys see like in the northern hemisphere, it's turning basically clockwise, and in the southern hemisphere basically counterclockwise. Right? So a little bit of Coriolis going on, isn't it? Just you change latitude. Right? All right, so there you go, ocean currents. All right, let's talk about phase changes. So I got a temperature versus heat energy diagram. Now, there's no numbers on this particular graph. It doesn't even say exactly what substance we're talking about, but we got to walk you guys through an example of water. Let's say you take an ice cube out of the freezer, which maybe is like negative 10 degrees Celsius. So like right here, guess where my mouse cursor is, negative 10 degrees Celsius. Okay? And you leave it out on the counter, it's gathering ambient energy, and it's warming up. So now it's negative 9 degrees Celsius, negative 8, negative 7. Now eventually reaches 0 degrees Celsius, and then it starts to melt. Okay? Now that melting process, well, it's a whole process. Guys, what happens to the temperature while it's undergoing melting? Who can interpret that graph? What's happening here? Guys, tell me, what's happening to the temperature while it's undergoing melting? That's not changing at all. It's stuck. You guys see it's like a flat line? You guys see it's a flat line right there? The temperature's not changing at all. Now, it's gaining energy. That's why we're going to the right on this graph. Now, overall, this graph kind of tends to go up and to the right, but it happens in stages. And at some point, it flatlines. And those points where it's flatlining, that's during the phase changes. So if you're on the far left of this leg right here, maybe you have 100% ice cube, and it's just starting to melt. Okay. And then maybe here you have 25% water, 75% ice. Here it's 50-50. Here it's mostly liquid water. Here's all liquid water. Okay. But the entire time, that entire ice mix, where the ice is melting into water, it's always stuck at 0 degrees Celsius. If you have a glass of ice water, I can tell you, I can guarantee what the temperature of your ice water is, even if it's been sitting around for half an hour. It's going to be stuck at 0 degrees Celsius. Now, I don't know exactly what the internal energy is. It might be closer to the left or close to the right. But I can tell you the temperature. The temperature is stuck at 0 degrees Celsius. Okay? And that's true until finally the last ice melts away, and you have all water. And now the temperature is allowed to increase with increasing heat energy. You see that? Okay. So now we're still putting energy into it. Maybe I put this on the stove now. Now it's on the stove. Now I'm putting in even more energy. Okay? And the temperature is changing proportionally. So beyond this point, if I double the amount of energy, I'm doubling, again, after this point, then I'll double the temperature and so on all the way up. Right? Right. Until you hit this point here, when the water starts to boil. Now down here in Florida, that would be, of course, 100 degrees Celsius. You guys said that earlier. Right? And then, oh, look, we are into another flat line. Guys, suppose you have some boiling water. See if you guys are following exactly what I'm saying. You have a pot of boiling water right here. Okay? Like, I want this food to cook faster. Well, I should probably turn up the temperature. So you reach the dial and you turn up the flame. Really turn it up, really hot. Make it really hot. Does that make your boiling water hotter? Yes or no? You guys are saying no. You guys are saying no. And you're right. The answer is no, because that's exactly what this flat line is right here. Right? Now, maybe I'm boiling it faster. I'm adding more energy faster, but the temperature's stuck because of flat lines. Right? Now, once all the water boils away into steam, if you could somehow keep heating that steam, that's this gas part right here. Right? Yeah, that's allowed to go over 100 degrees Celsius. So that's okay. Right? But the phase transitions, it's going to be stuck at some temperature. Okay, you guys got that? Now, what are the slopes of these lines, and how long are these flat lines? Like, how much energy does it take to completely melt an ice cube to boil it away? And what's the relationship between temperature and energy, say, during those phases, right? Now that depends on what material you're talking about. Because water is different than like copper, different from iron, different from, right? So I got some equations and I got some tables of materials. So let's look at these equations. See if you guys can read the music of these equations. I bet you guys know what most of these characters stand for, right? And then we'll make sense of this. We'll also do a little bit of math. Let me check my notes here. Yeah, I got a little bit of math we're about to do in the notes. See if you guys remember. Guys, what does delta Q stand for in this context? The change in, energy, heat energy. Yeah, okay. So guys, this week, capital Q is heat energy, which is quantified in some number of joules. And delta Q is like a heat energy transfer. Okay. What does delta T stand for? The change in temperature. Yeah. Okay. So if you change the heat energy, is the temperature probably going to change? Yeah, as long as you're not changing phase, right? Okay, again, that's the graph kind of going sort of up and to the right in generally, right? Does the amount of temperature change due to some heat transfer, does that depend on the mass? Right? Like, how about this? Suppose you have a little bottle of water and you have Lake Michigan and you want to raise each of those by 1 degree Celsius. Would that take different amounts of energy? Yeah. Right? So that's what this M is for. M stands for what? Mass. Right? Now, one final character. You guys see the C right here? Okay. That's specific to the material. It's called specific heat. Yeah. Wait, what is that? Yeah, specific heat capacity. So C, specific heat capacity. Okay. I'll come down to this other equation later. Actually, let's go ahead and look at this table. So here's different specific heat capacities for different materials. You guys see that? Right? Which basically tells you, let me scroll back. Okay. Oh, you could think of it like being the slope of this line. Actually, it's more like the inverse of the slope. Right? But basically, is the steep or flat, basically. Right? What's the relationship between temperature and heat while it's warming up, right? And here's a bunch of numerical values for a bunch of materials. Now, guys, look at that table. I got a question. What is the largest number on that table? What's the largest number on that table? Huh? What'd you find? This one all the way at the bottom. That's it. Water, 4,100 and something, is it? And the units go joules per kilogram Kelvin. Okay, so let's do an example. Example time. All right, you guys ready for some more notes? Notes time it's about to be. Check this out. All right, so let's try, I get rid of that. Let's do a transfer of energy, transfer of thermal energy. Wow. Start over again. All right. Leave myself some space. There we go. Delta Q. Okay, so this right here could be a transfer of thermal energy is equal to MC delta T. Okay? So here's mass. Here's specific heat capacity. And here's change in temperature. Okay. Let's work with that. Let's go with some numbers. What if the question is, how much energy would it take to boil, or no, scratch it, not even boil. Let's say to begin to boil a liter of water. Okay. Here, let's how much energy to begin to boil, because boiling itself is a separate process from this. Right? To begin to boil a liter of water. Okay. All right, let you guys catch up right there. That's right, everybody good so far? Okay. So delta Q, that's what we're solving for. How much energy do you have to transfer? Equals. Okay. Now 1 liter. Guys, how much? Isn't that a pretty good size bottle right here? Okay. How much mass do you think that is in terms of this kilogram? Hey, is that about this right here? This is about like a liter of water? I have my eyes closed, I might not be able to tell the difference. Yeah, I think we're talking about 1 kilogram. And oh, you guys were just looking at the table. You guys just told me that water had the highest number. And that was 4,186, wasn't it? That uh was it joules per kilogram Kelvin? Let me check. I should know that. I think it was. Ah, get this back here. It was, yeah, joules per kilogram Kelvin. Look at it right there. All right, so that's joules per kilogram Kelvin. Okay. By the way, the fact that it's the largest number on the table, I meant to mention this. What that means is that it's really, really hard to change the temperature of water. Like, for example, if I have, I'm going to draw this picture. I got this pot on the stove, a little handle here, and I fill this with water, goes on the stove. There's some fire on right there. On the, yeah, maybe I should make a stove range. Well, I already do the flame. I don't know, maybe both. Got some kitchen catastrophe. Because what gets hotter a lot faster, a lot easier? The metal pot or the water inside? Definitely the metal pot gets hot really fast. It takes a long time for the water to heat up. Okay? That is embedded in this number. In fact, it's the biggest number on that table of all those materials. Okay. Guys, what are you mostly made out of? You're about 2/3 what? Water. Ooh. And we're all warm-blooded mammals. We have to maintain a constant body temperature, right? Ah, yeah. So that's good thing we're made out of 2/3 water because it makes that a lot easier. The temperature of water is really, really stable. It's really hard to change the temperature of water. Okay? Now, to bring it to a boil, or to start to boil, can that be, maybe we call it 100 degrees Celsius? And have we been calling room temperature? Did we come up with a number for room temperature? I can't remember. It's been a long day. Let's do this. Can I call it about 72 degrees Fahrenheit in here? Is that okay? Okay. And if I subtract off 32 times 5/9, so that's about 22 degrees Celsius. Is that okay? 22 degrees Celsius probably in this room. Okay. Okay. And I want to get up to 100 degrees Celsius from 22 degrees Celsius. So we're going from room temperature up to boiling. Okay, all good so far? All right. Now let's check. Check the units. Kilogram, kilogram. That's a match, right? Oh yeah, go ahead. Yeah, that's joules per kilogram Kelvin. Yeah. So this kilogram, this kilogram. True. Yeah. Okay. Oh, right. I'm gonna have joules, which would answer the question because the question is how much energy, so that could be in joules. Okay. Oh, I'm just making sure all the units match. Oh, guys, what about this? Can I mix this Celsius with this Kelvin? Okay. Let me see. Show hands. How many guys think it's okay? I can punch this directly into the calculator as it is, and I'll get a perfectly valid answer. Who says yes? Yeah, I'm fine. Because, see, I could convert this to Kelvin first, but I'm just adding 273 there and also adding it there, and it just immediately subtracts from itself. Guess that? Right? So it doesn't matter. Okay. You guys remember earlier today? I said this is coming back. Remember I said, is a change in 1 degree Celsius the same thing as a change in 1 Kelvin? Remember that's the same thing? And that's what we got here. It's a temperature change. So this is perfectly fine. Yeah, so I'm just going to throw this in a calculator. So let's go 1 kilogram times 4186 times whatever 100 minus 22 is. I'm looking at 326,500 something joules. Woo! Right. So that might represent how much propane you had to buy if it's a flame. That might represent how much energy you have to buy from the utility company. This is a range. Okay. That's how much energy it takes to bring the water to begin to boil. All right, you guys got that? All right, so back over to PowerPoint. All right, so that's this top equation here. We just applied that one. Everybody good there? Okay. Now, what about this bottom one? Do you see anything about a temperature change down this bottom one? No. Oh, guys, if there's no temperature change, what part of the graph do you think that second equation refers to? How about one where the temperature doesn't change, right? Either while it's all melting or all boiling in the material, right? And that's called either heat of fusion down here where it's melting or heat of vaporization up here where it's boiling. You guys get that? Okay. So let's check this out. Depends how much mass we have. Maybe we got a kilogram of water, right? And now this delta H is, I got a table for that too. It's right here. You guys see specific latent heat of fusion? That would be like melting an ice cube, or freezing it, go the other way, right? Or specific latent heat of vaporization if you're boiling it or condensing it the other way, right? Okay, water's right on the top, so you guys can see from water, right? So if I wanted to boil away the water, I'd have to do also this equation right here. So we just did the top equation, got what 300 something thousand joules, right? But if I want to keep boiling it, I have to run to the second equation, and that takes even more energy, and I have to plug in this number here, the 2258 kilojoule per kilogram. Right, you guys that? All right, what else I got here? Let's look at this phase diagram. This one's really cool. Now, this specifically applies to water because water is one of these substances you can commonly see in the three main states, solid, liquid, and gas, right? But notice that the phase of water does not just directly depend on temperature. It also depends on pressure, which is an easy variable to forget about. So let's look at this big old map here. You see going across horizontally is different temperatures. You got 0 Kelvin, which is absolute zero, 50 Kelvin, 100, 150, 200. See, it's scaled linearly, 50 Kelvin at a time. Or all the way at the bottom, it's in terms of Celsius, which is the same scaling, just different numbers. Okay. Okay. I see two red lines running vertically. One is at 0 degrees Celsius, one's at 100 degrees Celsius. So the room temperature in this room is, well, probably about a quarter of the way, maybe they're about there. Okay. Now let's check out pressure. Pressure. Now that goes vertical. But the pressure scale's doing something weird. Guys, look at this. 1 Pascal, which you guys know is 1 Newton acting on 1 square meter, right? 1 Newton per square meter. It goes 10 pascals, 100, 1,000, 10,000, 100,000. Whoa, guys, is that going by factors of 10? Is that linearly scaled or is that logarithmically scaled? It's logarithmically scaled, isn't it? It's by factors of 10. Because if you scale that linearly, this graph would be like the height of the Empire State Building. Wouldn't make any sense, right? All right. So now what? Oh, so I think. Do you guys see? Here's a question about pressure too. Who remembers from last semester? How many pascals of pressure are you sitting in right now? Which is 1 atmosphere. 1 atmosphere equals 100,000 pascals. You guys remember that? It's like 101,000 something, right? And that's this red line going across. You guys see this red line going across? Okay. So does everybody see where my mouse cursor is right here? Right. That's what we're in this room right now. So this is 1 atmosphere pressure. This is also room temperature. Okay. Now, if I asked you guys to boil some water, there's 2 ways to do it. One way is you could heat the water up. And that'd be like going to the right on this graph. But who sees the other way that you could also boil water? That's maybe less obvious. You don't have to change the temperature at all. You could change the what? Pressure. Aha. Okay. Guys, could you cut straight down and also boil the water just by reducing the pressure? Okay. I have well, spelled belt ring. Here, I have a demo for you guys, but I know we're about to run out of time. This is reduced pressure boiling. Now, boiling is a process that takes the energy out of the system. So it does cool it down. So if you touch that boiling water, it starts off room temperature, and then it gets cold, and then with a layer of ice. All right, so we're going to have to pick up there tomorrow. You guys have a good night.